Mirrors is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in the last chapter we dealt with reflection and refraction, and we're going to pick up right where we left off in this chapter on mirrors and lenses. We'll cover mirrors in this lesson and lenses in the next. Now we're going to talk about both plane mirrors as well as spherical mirrors in this lesson, and the two types of spherical mirrors, both concave and convex mirrors. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So now we're ready to deal with plane mirrors here, and what we want to do is draw some ray diagrams so we can discover where the actual image is being formed. So now we're going to define a couple of things. Now, the distance from the mirror to the object is going to be called the object distance, and then the distance from the mirror to the image is going to be called the image distance. Now, it turns out for a plane mirror, we need two rays to kind of identify where that image is going to be. So, and it turns out it could be any two rays you draw to the mirror, but there's two that are pretty convenient here. And the first one is going to be one directly head on here. So, and if we hit a plane mirror head on, then it's going to get reflected right back as well. And there's a reflected ray. Now, again, we could pick any other reflected ray here. So, but the one I'm going to choose is going to be one that goes kind of to the midpoint of this mirror here, because it's going to be able to identify that law of reflection, that the angle of incidence is going to equal the angle of reflection as well. All right, so now we've got two rays drawn, and these two reflected rays in blue, if you look, the further we get away from the mirror, the farther and farther apart they get. They're never going to really intersect, and we're not going to form a real image. And that's true for a plane mirror. For a plane mirror, you never form a real image. Your image is always going to be virtual, as we'll see. So these light rays don't really intersect, but they do appear as if they had come from a common point back here behind the mirror. Right back here. So, and that point right there is the image, and in this case, again, the light rays aren't really intersecting. In fact, there's no light rays behind the mirror at all. The reflective surface is all over here, so, but it appears as if they came from that point, and so that's a virtual image. So, and it turns out, again, for a plane mirror that the image is always virtual. Now, a couple other things we can identify here. So one, so when the image forms on the same side of kind of this midpoint of the mirror as the object itself, so the object here is above that midpoint, so is the image. That's evidence you're going to have an upright image as well. So we'll find out in a little while that for any single mirror or any single lens, virtual images are always going to be upright, and real images are always going to be inverted and upside down, and we'll kind of see why that is with some of the other ray diagrams. But for a plane mirror, the images will always be virtual and always be upright. Now, a couple other things we can identify here. So again, we talked about the image distance and the object distance. So again, the straight line distance between the object and the mirror, that's called the object distance. We often use P, or some books DO. I'm going to use P. So for the rest of this lesson. And then the distance, the straight line distance from the mirror to the image location, that's going to be Q, or some books will use DI. Now personally, I kind of like DO and DI because it's not difficult to remember what those stand for. But P and Q is a real common convention, and the ones I'm going to use here, because probably the majority of textbooks use that. So P and Q, object distance, image distance. Cool, now for a plane mirror, it turns out that the object distance and the image distance are always equal as well. So if you're standing in front of a mirror, and let's just say you happen to fall asleep while standing in front of the mirror and you wake up, and your initial instinct is that somebody who looks a whole lot like you is standing a little ways away. Now, if you're 3 feet in front of a mirror, what it looks like is that there's somebody who's 3 feet behind the mirror looking back at you, because again, this image distance is always going to equal the object distance for a plane mirror. And so for a plane mirror, you're always going to have an image behind the mirror. It looks like it's the same distance away as the object is to the mirror. So, and it's always going to be a virtual and upright image. Now, one other thing we should talk about is the magnification is also going to be 1. And what that means is that the image is exactly the same size. It appears to be the same size as the actual object. So we'll find out that magnifications that are positive are going to be for upright images, whereas magnifications that are negative are going to be for upside down or inverted images. We'll find out that magnifications that have an absolute value that's bigger than 1 look bigger than the actual object. So, and magnifications that are the absolute value smaller than 1 means the image is going to look smaller than the actual object. So positive versus negative, and then absolute values bigger or smaller than 1 are the keys there. Now, one thing to note, and you've probably noticed this every time you look in the mirror, is there's this left-right reversal. If you're standing in front of a mirror and you raise up your left hand, in the mirror it looks like the person staring back at you is actually raising up their right hand, and so on and so forth. So again, it's still an upright image. There's no top-bottom reversal, if you will, but there is a left-right reversal for a plane mirror. So the rest of this lesson, we're going to focus on spherical mirrors. And again, there are two types, concave and convex. And again, the concave refers to the fact that the reflective silvery finish is on the concave surface, the convex the opposite. And so here's an example of a concave mirror, and let's see if we can actually get the camera in view there. And you can see there's my camera, it's on the tripod, and it's inverted. We'll come back and talk about that in just a little bit. So, and here is an example of a convex mirror, and you kind of might recognize seeing these in stores and stuff like this to prevent theft, and they're kind of up and give a wide field of view and stuff like that. So we'll come back to that as well. Now, it turns out with a concave mirror, there are two different scenarios that we need to talk about. And so one of them is when your object distance is greater than the focal distance. One of them is when your object distance is less than the focal distance. And you might be like, what, Chad, what was that, the focal distance or focal length it's called? And yeah, we got to talk about that for just a second. It turns out that the focal length or focal distance is equal to 1/2 of the radius of curvature. And so when we're drawing ray diagrams for these lovely mirrors, we often draw what's referred to as the principal axis right down kind of the horizontal middle of the mirror, right to where the mirror is perfectly vertical, if you will. So, and it's perpendicular to that vertical point. And there's our radius of curvature, where we've got this lovely radius all the way around. Well, halfway between the radius of curvature and the mirror is where you're going to find this focal point. We'll kind of highlight it on both of these right about here somewhere. And again, it's exactly half of the radius of curvature. Now, what that focal distance is, you can kind of think of this. If you had an object, and we're going to use this little lovely red rectangle here, but let's say it was infinitely far away from this mirror. Well, what you'd find out is that the light rays reflecting off the mirror would all intersect right at that focal distance. That's exactly what would happen. We can see why that happens if we take a look at the other piece of math we're going to be using quite a bit here, and that's called the mirror equation. So 1 over the object distance plus 1 over the image distance equals 1 over the focal distance. We're going to use P's and Q's, but again, some textbooks like to use DO for the object distance and DI for the image distance, and personally that's my preference, but this is probably used a little more commonly, so I'm going to stick with it. But if you look, if the object is infinitely far away, so effectively P is infinity here, well, 1 divided by infinity is 0, and that term effectively goes out of the equation. And the only way the remainder of this equality would hold true is if Q equaled F, if the image distance equaled the focal distance. And so when the object is infinitely far away, so the image will form at the focal point. That's kind of the idea there. So that's kind of an idea of giving you an idea of what that focal point is, but it turns out it's a valuable piece of information for doing calculations with mirrors, and we'll find out for thin lenses in the next lesson as well. All right, so we're going to set up drawing some ray diagrams here. And so again, with a concave mirror, there's two scenarios. When your object is beyond the focal distance, like in this first one here, we're beyond that focal distance away from the mirror. And then when your object is closer to the mirror than the focal distance, which is this scenario here. So we'll find out that with the concave mirror, so when you're beyond the focal distance, the image is going to be inverted and real. And that's why when I held up the concave mirror, the camera appeared to be upside down. It was inverted because right now we're, from where I was standing, we were beyond the focal distance of that mirror. Now, the other scenario is when the object is placed within the focal distance like this one here. And in that case, we're going to have an upright but virtual image instead. And then we move on to talking about the convex mirror. It turns out there's no two scenarios for that one. Regardless of where you place the object, you are always going to get an upright and virtual image. And so I've kind of given you kind of where this lesson's heading. We're going to explain why these happen, but I kind of wanted you to upfront know these three different situations you might encounter, because qualitatively you can say some things about what you should expect about the image long before you ever do a calculation. Okay, so we want to start by drawing some ray diagrams. And so it turns out we want to draw some rays, and again, we're trying to see if the rays actually or really intersect, and if they do, these reflected rays, then we're going to have a real image. But if they don't really intersect, we'll end up with a virtual image, a point where it looks like the rays actually originate, but they don't. All right, so let's see how this works. So there's common to draw 3 different rays, and it turns out if you actually can draw 2 of the rays, that's usually enough to identify where the image is going to be located. So first one we're going to draw here is going to be parallel to the principal axis. And so I'm going to choose the very top point, but it turns out, I mean, every point on this lovely object is going to be reflecting rays and stuff like that. But I'm just going to show the ray diagrams coming off the top point here. The first ray we're going to have is going to be parallel to the principal axis. You might recall the law of reflection, that the angle of incidence equals the angle of reflection. And if we kind of looked at the angle of the mirror right here, and we could draw then the normal to it, we could draw an incident angle and then the reflected angle. And it turns out you could work it out and find out that the reflected angle is going to go right through here. Now, again, we're eyeballing this a little bit, but rather than kind of having to examine it that way, what you're going to want to do is probably just remember where these rays go. And the first one, parallel to the principal axis, is the incident ray, and the reflected ray is going to come out through that focal point. That's ray number 1. Now the second one is going to kind of be the opposite of that. So, and that ray is going to go through the focal point. So, and then the reflected ray is going to come out parallel to the principal axis. And so it's kind of the opposite. All right, well, if you notice, these 2 rays are really intersecting right at that point right there, and that's going to be where the image is located. And because the light rays are really intersecting, that's what's going to make it a real image, as we'll see here in a second. So now again, 2 rays is really sufficient, but most textbooks and professors are going to recommend that you draw a 3rd ray as well. So, and there's a couple different options, but the one I choose is to draw right to the principal axis. And so we're going to go right to the principal axis. So, and in the right to the point, at least where the principal axis intersects the mirror. And because the principal axis is perpendicular, that is the normal. So, and the incident angle is going to equal the angle of reflection in this case as well. And so it's going to be the exact same angle. And there it is, where the incident angle equals the angle of reflection. And you can see that all 3 of the rays we've drawn intersect at a single point, and that is a real image. So because the reflected rays are really intersecting, that's a real image. Now here's the deal though. So if we draw kind of where this is going to be located here, so it's going to be something like that. And what you're going to find out though is that in this case, so the top point of our object, the light rays are reflecting to form kind of the bottom point of the image. What you find, this thing is completely inverted. And what you find out as well is that all the time, a real image is always going to be inverted. And so in this case, inverted and real always go hand in hand. And we're going to find out that upright and virtual always go hand in hand as well. And so it's convenient that we can kind of remember this with IR and UV, both parts of the electromagnetic spectrum. So inverted images are real images are inverted. Upright images are virtual images are upright. Those go together. Now it turns out we can say that they always go together if you're dealing with a single mirror or a single lens. Now when you start dealing with combinations of mirrors and lenses, all bets are off, and this may or may not hold true. But for any single mirror lens, which is what we're going to deal with in this chapter, so largely that's what's going to hold true. Real images are inverted, and virtual images are upright. Okay, and now we can see why that is. So if we go and compare this now to our second scenario, where the object distance now is closer than the focal point, so we can draw our light rays once again. And the first one again, same diff. We're going to draw one coming in parallel to the principal axis, and it's going to get reflected back out through the focal point. Right there. So no difference there. The second one is really going to be the same thing as the second one we drew over here as well, but it's going to feel just a little bit different because we want to draw through the focal point and then come back out reflected parallel to the principal axis. But we can't actually go through the focal point because we're closer than it. And so what you actually have to do is kind of draw as if you were going from that focal point instead. And then that light ray is going to come back parallel to the principal axis. And we can see here that these 2 reflected rays are only getting farther and farther apart. They are never going to intersect. There's no real image here whatsoever. Now, if we draw one more of these here, so In this case, we can draw one more, and we're going to draw it right to where the principal axis intersects the mirror again. And once again, that angle of incidence is going to equal that angle of reflection. And again, these light rays are only getting farther and farther apart. They're never going to intersect at a common point. But what you can do is kind of like extrapolate back and see that they look like they all came from a common point behind the mirror. Now, did the light rays really originate from that point? No, they didn't really. And that's why they call this a virtual image. The light rays don't really intersect there in this case. All right, so a couple of things here. When you go to solve for Q, the image distance in the mirror equation here, so it turns out when you get positive values for Q, that's going to be an indication you've got a real image. When you get negative values for Q, that's going to be the indication that you have a virtual image. And so we can see it with the ray diagrams, or we can see it mathematically with the mirror equation for the values of Q being either positive or negative. All right, now we also want to take a look at this equation for magnification here. And so magnification is the relative ratio of the height of the image relative to the height of the object. If the image is bigger than the object, you get a magnification that's bigger than 1. If the image is smaller than the object, you get a magnification that's less than 1. Now I say greater than 1 and less than 1, but what I really should say is that the absolute value of the magnification is larger or smaller than 1. Because it turns out these magnifications can also be positive or negative. So here's the way it works. If the absolute value is bigger than 1, the image is bigger than the object. Okay? If the absolute value is less than 1, then the image appears smaller than the object. But now positive versus negative. If the magnification is positive, that's going to be an upright image here. So we'd see over in this case. Now we haven't talked about it, we just said it was virtual, but it's also for virtual images, they're going to be upright as well, and we'll see why here. So in this case, the object is above the principal axis, well, so is the image. And that image is going to be right side up, if you will, as well. And so both the object and the image are right side up, that's an upright image. Whereas in this case, the object was above the principal axis, the image would be below the principal axis. That's why it's an inverted image. All right, now going back to magnification then, if your magnifications are positive, that's a real image. If your magnifications are, if magnifications are positive, that's going to be an upright image. If your magnifications are negative, that's going to be an inverted image. And we'll find out now why inverted and real always go together and upright and virtual always go together. Because it turns out if you work out the geometry here, this ratio of the height of the image to the height of the object can also be solved with negative Q over P, the image distance over the object distance. We can kind of make this make a little sense of why the magnification should be proportional to the image distance. So if you look at putting a projector and showing a big projection up on the wall and stuff like that, you can make that projection bigger and bigger if you move the projector further and further from the wall. Or if instead of it being a wall, let's say it was just a mobile screen, you could move the screen further and further away from the projector. In either case, the image that's being projected on the screen is traveling farther and farther to get to the screen. And that's the key. The farther the light has to travel to form that image, the larger it gets. And if it travels far, the light travels farther to form to where the image is located relative to where the object is located, you get a magnification that's going to have an absolute value bigger than 1. So that's kind of why this makes sense in this case. But it's negative Q over P. And again, if the magnification overall comes out negative, it's an inverted image. If it comes out positive, it's an upright image. And so now we can kind of put this all together. So Q, we said, if that's positive, that means you've got a real image. Well, the object distance is always positive. So for any single lens or mirror, it's always going to be positive. Now, again, if you use some certain special cases where you've got combinations of lenses or mirrors, you might end up with some situations where that is not defined as being positive. But for anything you're going to see in this course, so that object distance is going to be positive. So if Q is positive, i.e. it's a real image, and P is always positive, by the time you factor in that negative sign, the magnification is going to come out negative, and your real image with a positive value for Q is going to end up with a negative magnification and therefore be inverted. And that's why real images are always inverted. Now it works the opposite as well. So let's say you've now got a virtual image. Well, a virtual image is indicated by the fact that you've got a negative value for Q. And a negative times a negative, all divided by a positive object distance, is going to give you a positive magnification. And so the negative value for Q, again, tells you have a virtual image. The positive value for the magnification tells you it's an upright image. And that's why virtual images are always upright. And that's why these go together. Cool. So those are our two scenarios for concave mirrors. So let's kind of see how this plays out with a cool little demo here. All right, so we're going to use the current book I'm reading called Peace Child by Don Richardson, which I'm really enjoying. It's kind of a convenient way to look at this, and you can see that it currently is inverted because we are beyond the focal point of our concave mirror. But as we move closer and closer together, well, it turns out we're going to approach that focal distance. And when you reach that focal distance, it turns out that the image gets infinitely large and is unrecognizable, kind of somewhere in that ballpark. And then when you get past that point, so all of a sudden now the image is no longer inverted, it's upright. So, and it gets smaller and smaller as you then get closer and closer to the mirrors. So from this point on, this is kind of where we use like vanity mirrors. They're kind of used for magnifying so we can see all the blemishes in our face, because apparently we like doing that for some reason. So, but once you get to that focal point again, the image gets infinitely large, and on the other side of it, we're now back to being an inverted image instead. So now let's just briefly explain what's going on mathematically to match our observations with the book in the concave mirror. So in this case, when you're infinitely far away, when your object distance is infinity, again, your image is going to form right where the focal point is, as we kind of have already stated. Now, but if you look at the magnification equation, so when p is infinity, effectively, as p approaches infinity, your magnification is going to approach 0, because dividing by infinity gets you 0. But as you bring that object closer and closer and closer together, p is going to go down, and your magnification, the absolute value anyway, is going to go up. Now, as long as you're beyond the focal distance with that object, then when you solve for the values of q, you're going to get positive values indicating that's a real image. And if you plug in a positive value for q, the magnification is going to be negative, showing that it's inverted, just like the book was inverted when we were further away. But once you actually have p approaching a value of f, you're approaching that focal distance. So when the object right gets onto that focal distance, that's when we couldn't resolve the image of the book anymore. And so if you look, if 1 over p and 1 over f are equal, well, the only way that's true is if 1 over q equals 0. Well, if 1 over q equals 0, that means q is going to be infinity. The image is forming at infinity. Well, you can't really get to infinity, right? So there's no real image that's viewable there. But also, if q is approaching infinity, the magnification is approaching infinity as well. So the object's getting infinitely large, but the image is forming infinitely far away to where you can't really resolve it. So that's what's going on. But once you get to the other side of that focal distance, when the object's inside the focal distance, now all of a sudden you're going to get negative values for q when you use the mirror equation, indicating that it's a virtual image. And when you plug in the negative value for q in the magnification, you get positive values for the magnification, indicating that you had an upright image as well. And it turns out once you cross that focal point, so as close to the focal point as you can be, but having crossed it closer, you got the biggest image you're going to get, and it's magnified. It's actually, the image is bigger than the object. So, but as you get closer and closer and closer to the mirror, that image is going to get smaller and smaller and smaller, but it will still be magnified relative to the original object. Those magnifications will be larger than 1. So now we're going to take a look at our convex mirror. And again, you might look at these as kind of being security mirrors, but sometimes you'll see these kind of on the passenger side rear view mirrors in your car and things where it says things may be larger than they appear. So, and that's because in a convex mirror, so your magnification is always going to have an absolute value that's less than 1. Your image is always going to appear smaller than the actual object. Now, it turns out there's not two scenarios here, so it doesn't matter where you're located. It doesn't matter if you're within the focal distance or beyond the focal distance or anything of that sort. So with a convex mirror, the image is always going to be upright and virtual, and it's always going to be appearing smaller than the actual object. So again, it doesn't matter how close or far you get. So you can kind of see my camera there on the far wall there, and it's upright the whole time. So because we have an upright virtual image the entire time, that always appears to be smaller than the actual object. All right, so a couple things we should know here. So one, we're not going to really form an image. So there's no real image. The reflected rays are not going to intersect over here on this side of the mirror. And so if you recall in the last example with the concave mirror, when the image formed behind the mirror, so to speak, it was a virtual image. The light rays didn't really intersect there. And same thing is going to be true here in a different respect. So there's our radius of curvature, and halfway to our radius of curvature between the radius of curvature and the mirror is going to be the focal distance. And just like we saw when the image formed on the back side of the mirror, well, in this case, the focal point's on the back side of the mirror. And it turns out with a convex mirror, you need to make sure that when you plug your value for the focal length or focal distance into the mirror equation, that it is a negative value. Even if you're not provided with a negative value, if it's for a convex mirror, it's a negative value, and you've got to plug it in as a negative in the equation. Super important. All right. That's the first thing. So if we draw our light rays now, so it turns out we can draw exactly the same set of light rays. First one we're going to draw is going to come in parallel to the principal axis. So, and if you recall, before we said it gets reflected out through the focal point. Well, that's not possible. The focal point's on the other side of the mirror. But it's just as if it came from the focal point in this case. And there's our reflected ray. So next one we're going to draw it towards the focal point. We'll never get there because we'll bump into the mirror first, but we're going to draw it just as if we were going towards that focal point right there. And then that one's going to get reflected back out parallel to the principal axis. And we can definitely see that these two reflected rays are definitely not going to intersect, but they do look like they came from a common point behind the mirror again. And one more we can draw towards the principal axis itself, or where the principal axis intersects the mirror. So, and the angle of incidence equals the angle of reflection. So where this angle equals this angle. And once again, we can kind of work our way backwards here. There's that one, that one, that one, and they intersect at a common point right there. And that is our virtual image. The light rays don't really intersect there. They just look as if they all originated from that point. And once again, when you've got a virtual image, that's going to be a negative value for Q when you solve for it in the mirror equation. And when you plug it into the magnification, a negative value for Q is always going to end up with a positive magnification, indicating again that your virtual image is always going to be upright. Cool. And again, didn't matter where we place the object. If we're closer than the focal distance, farther than the focal distance, it totally doesn't matter. One thing you should also know, though, is that no matter how you work this out, your image distance is always going to end up less than your object distance. And because your image distance ends up less than your object distance, your magnifications are always going to have an absolute value less than 1. And in this case, we could just say less than 1 because they're always going to be positive as well for a convex mirror. But in this case, they're always going to be less than 1 because the image always appears smaller than the actual object. So now we're going to do some math with this, and we're going to use the mirror equation and the magnification equation in every one of the following 4 examples. The first 3 are going to be dealing with a concave mirror, the last one with the convex mirror. And so the concave mirror, we're just going to be moving an object slowly closer and closer and solving for the image distance every time. So first question says an object is placed 12 centimeters in front of a concave mirror, and in parentheses it tells us that the focal distance is 4.0 centimeters. Where's the image located? Is it real or virtual, upright or inverted? And what is the magnification of the image? And so in this case, we go to plug this into the mirror equation. We're going to have 1 over the object distance, which is 12 centimeters. So plus 1 over Q, which is what we're going to want to solve for. And the focal distance was given as 4.0 centimeters. So, and we could solve for Q. Now, a couple things here. So it is a concave mirror, and we are at an object distance that is greater than the focal distance. Well, if you recall, we said that's when you're going to get a real inverted image. And so before we even solve for Q, if you qualitatively understood what we did with that concave mirror and be like, oh, if you're beyond the focal distance, real and inverted. If you're closer than the focal distance, then it's upright and virtual. Then you could have answered at least the qualitative parts of this question already. But where is the image located? Well, that's what is, that's what Q is. And so in this case, we'll have 1 over Q equals 1 over 4 minus 1 over 12. And one thing to note, you might be like, hey, Chad, you need to convert centimeters to meters to get SI units. Turns out, as long as you're consistent in your units, you can use any units of length you want to. And it's going to be a lot easier to do the math here in centimeters than it would if we plugged in like 0.12 meters and 0.04 meters. So I'm going to leave this in centimeters. And if you notice 1 over 4 minus 1 over 12, my lowest common denominator here is going to be 12. So in this 1 over 4, I'm going to multiply by 3 over 3. That way I get a total of 3 over 12 minus 1 over 12. And so 1 over Q is going to equal 2 over 12. And so flip both sides back over, and Q over 1, or just simply Q, is going to equal 12 over 2, or 6.0 centimeters. All right, so we've solved for Q, 6.0 centimeters. We can also solve for the magnification. Magnification equals negative Q over P, which in this case is going to be negative, and in this case 6.0 centimeters. The object distance was given as 12 centimeters. We can see this is going to equal negative 1/2. All right, so if we didn't already realize that this is a real inverted image, we'd now know this. Because Q is a positive number, that's a real image. So because magnification is a negative number, that's an inverted image. So, and there we go. The fact that the absolute value is less than 1 also tells me that the image is smaller than the object had it been asked. All right, so the second question should look nearly identical to the first one, except we're placing the object at a different distance from the mirror. So it says an object is placed 6.0 centimeters in front of a concave mirror, in parentheses f equals 4.0 centimeters. Where is the image located? Is it real or virtual, upright or inverted? What is the magnification of the image? So it's pretty much the exact same set of calculations, except in plugging in for p, it's not going to be 12 centimeters anymore. It's now going to be 6 centimeters instead. So 1 over 6 plus 1 over q equals 1 over 4. So if I solve for q, 1 over q is going to equal 1 over 4 minus 1 over 6. Get your common denominator, which in this case, your lowest common denominator would be 12. You could also technically use 24, but I like 12. And so to get that, I'm going to multiply the first term by 3 over 3, second term by 2 over 2. We're going to have 3 over 12 minus 2 over 12, which is 1 over 12. So in this case, 1 over q equals 1 over 12. And easy to see that q is going to equal 12 centimeters. Your magnification is equal to negative q over p, which in this case is going to be negative 12 centimeters over 6 centimeters, which is going to get us negative 2. All right, so once again, we are still at 6 centimeters further than the focal distance on a concave mirror. So we should still get a real inverted image. And so we can see that. So with Q being positive, that's a real image. With the magnification coming out negative, that's an inverted image. So the big difference here is with it being negative 2.0, so because the absolute value is bigger than 1, that means the image is now larger than the object. In fact, it's double the size of the original object. So this is something that's now being magnified overall. All right, third question is going to be really similar to the last two, but we're going to move it in a little bit closer, and this time it's going to be within the focal distance. Question says, an object is placed 2.0 centimeters in front of a concave mirror. Focal distance equals 4.0 centimeters. Where is the image located? Is it real or virtual, upright or inverted? What is the magnification of the image? And so once again, so what's going to change is p, and p is now going to be 2.0 centimeters plus 1 over q equals 1 over 4 still. And now things have changed. We're now closer than the focal distance. And for a concave mirror, if we're closer than the focal distance, we're no longer going to have a real inverted image. We're going to have an upright virtual image instead. And so we could answer the qualitative parts of this question before ever doing the calculation if we remember that pattern. But let's solve for this one more time. And so in this case, 1 over q is going to equal 1 over 4 minus 1 over 2. Lowest common denominator here is going to be 4. Multiply this term by 2 over 2. And we're now going to have 1 over 4 minus 2 over 4. And so 1 over q is going to equal negative 1 over 4. And so q equals negative 4.0 centimeters. Your magnification, which is equal to negative q over p, is going to equal negative times negative 4.0 all over, and again, your distance here is always positive, so 2.0, but a negative times a negative means we're going to get a positive magnification, in this case, positive 2.0. We can see things have changed here. So first off, your Q value came out to be negative. So that means your image here is forming behind the mirror, not in front of the mirror. So it is a virtual image, in this case having a negative value of Q. Also, your magnification came out positive, which means it's going to be upright, not inverted. But again, once you knew it was virtual, you knew it was going to come out upright. Those always go together. And then again, your absolute value of magnification is larger than 1. So this is an image is going to be larger than the object. And again, in fact, it's going to be twice as large as the object. All right, so our final mirrors calculation here. Question says an object is placed 2.0 centimeters in front of a convex mirror. Focal length is given as negative 4.0 centimeters. Where's the image located? Is it real or virtual, upright or inverted? What is the magnification of the image? So same set of questions. Now, once you realize this is a convex mirror, a couple things you should know. One, the image is going to be upright and virtual every time, and that your image is going to be smaller than the object every time as well. So those are always true for a convex mirror. One other thing is you should always remember for a convex mirror, the focal distance is going to get plugged into this equation as a negative number. Even if they don't give it to you as a negative, and sometimes what they'll do to trick you is they'll give you the radius of curvature. And they'll just say the radius of curvature equals 8 centimeters. And you'd have to remember like, oh, well, the focal distance should be half that, but half that and negative, even if they didn't give you the radius of curvature is negative, which they kind of probably should have. But if they didn't, you still have to know the focal distance should be negative for a convex mirror. All right, so let's do some plugging and chugging here. So 1 over p, and once again, it should look pretty similar to this last calculation here. So 1 over 2.0 centimeters plus 1 over q equals 1, not over 4.0 centimeters, but over negative 4.0 centimeters. And so in this case, we're going to have 1 over q equals negative 1/4 minus 1/2. And so 1 over q, you got to get your common denominator again, which is still going to be 4. Got to multiply this second term here by 2 over 2. And so you're going to have negative 1/4 minus 2/4, which is going to get you negative 3/4, which means that q is going to equal negative 4 over 3. If we go to get our magnification, it's negative q over p, which in this case is negative of negative 4/3 all over our object distance of 2, which is going to get us positive 4/6 or positive 2/3. Okay, so q came out negative, again confirming what we already knew should be the scenario with a convex mirror, that we're going to have a virtual image. So if you have a virtual image, our magnification came out positive, which means the magnification or the image is going to be upright. So, and again, the magnification has an absolute value less than 1, which means the image is indeed smaller than the original object, confirming all of our suspicions regarding a convex mirror. If you have found this lesson helpful, consider giving it a like. Happy studying.